With more EVs on the road than ever, it's important to think not just about range, but how those vehicles actually achieve that range. To help sort through the noise, we visited Lucid Motors in Newark, California to get a deep dive on how efficiency keeps EVs on the road longer with less charging and is one of the main solutions to building a $25,000 EV. I am here with Lucid Motors CEO and CTO Peter Rawlinson. Peter, thank you so much for having me today. Sure. Recently Lucid had some news about miles per kilowatt hour, 5 miles per kilowatt hour. Mm-hmm. That's sort of big news, but I don't think the average person when they're thinking about EV thinks about that. They're still thinking about range. Range is the one metric that they seem to be interested in.
Totally.
But the reality is that miles per kilowatt hour, that's an efficiency metric and something people should really start thinking about.
Totally. Well, I mean, it's the customer sees range, mm-hmm. but there are intangible values of how you create that range. Mm-hmm. For example, up until very recently, the world believed that range is just a function of how many batteries you stuff in the car.
Yeah.
And Lucid challenged all that. When we built Lucid, back in 2016, we really challenged that notion. Could we go further with less batteries? And this is kind of a radical notion at all. And it's absolutely based upon, could we create a more efficient propulsion system, motor, inverter, and the whole system? Mm-hmm. And there was this mindset that you couldn't improve upon the efficiency of an electric motor. It was kind of been like it has been since Victorian era, and it's kind of like a universal constant. Mm-hmm. It's like Einstein based upon Maxwell's work of the universal constant of the speed of light. All relativity is based upon that. And there was this notion that all EV tech was based upon you couldn't do a better electric motor, mm-hmm. so you want to double the range, you double the number of batteries. So everything gets better if you can actually go further with less batteries. Mm-hmm. It costs less in your pocket, there's less draw of electricity on the grid, and there's actually more room in the car for your feet, which is an important factor. Mm-hmm. Someone once said to me very recently, your car's quite high-end cars, Peter. In that marketplace, people don't care about efficiency. And I said, why do you say that? Do you think they care about foot room and comfort? Oh, they want that. I said, well, efficiency gives that because there's less batteries, so you can actually put your feet in a comfy position. So there are intangible values.
Yeah.
So although the customer just sees range, the way we create range is of profound importance, and it's an absolute cornerstone of mankind's transition to a sustainable mobility future.
And with this range, which again is sort of intricately added to the efficiency, and you say that person is like, well, people don't worry about the efficiency of electric vehicle. The reality is they sort of do.
Totally.
Because they don't want to stop every 200 miles. They paid a lot of money for a luxury vehicle. They want to go as far as possible.
Yeah. So efficiency is an enabler for range in a vehicle which is viable both technically and financially. And because the battery pack has a disproportionate impact upon the cost of building an electric car. For a family car, the battery pack alone can contribute over 40% of the value of the cost of the bill of material. That's the cost of all the parts that the automaker has to bring together to build that car. So this is of profound significance. And what we've done, first of all, we're the first company to get over 500 miles range. We did that largely through efficiency without a disproportionately large battery pack. And now the next step is to use that efficiency advantage to help make more affordable cars that can go reasonable range, maybe 250, 300 miles range in the future, with an extraordinarily small battery pack, which will bring down the cost.
And so let's talk about how range is efficiency is sort of measured and communicated with drivers now. The MBGE.
Yes.
This idea of gas and electricity and how that all works together.
MPGE, which is miles per gallon equivalent, and we're getting with the Lucid Air Pure rear-wheel drive 146 MPGE, which is, as far as I know, a world record. Now, I actually think this is a very weird construct because it's based upon the notion that 1 gallon of gas, I think, has got the energy of about 33.7 kilowatt hours. I can't, forgive me if I've got that wrong. I'm trying to erase this from my memory. It's so obtuse. The problem is this is supposed to help customers, but actually I think it does customers a disservice because all these numbers are crazy big. You can have an electric car with 98 mpge. It sounds fantastic, but it's pretty poor actually.
Yeah. Because it does, and but I think the idea is that, well, everyone knows what MPG is. So it's just these giant numbers. But the cost of electricity is different.
Totally.
The way the vehicles work, they're far more efficient. It's just such a weird.
It's a weird and artificial construct, and I think it's so weird it does everyone a disservice. So then the other thing they do is measure watt hours per mile. That's another thing you see on cars and on stickers. Now, this is a measure of consumption. It's not a measure of efficiency, and that is actually it's 1 over efficiency. It's the inverse of consumption, is the converse of efficiency. That is it's not how far can I walk if I've had a pint of beer. It's how many pints of beer do I need to drink to sustain that walk. And it's a very weird thing. I think it's really important in my position that I try to make more of these constructs more relatable and understandable and convey a better message. Now, I think most people understand miles per gallon of gas.
Yes.
And I wanted to create the new miles per gallon. So it's very simple. We create the new miles per gallon, which is miles per kilowatt hour. That is the new miles per gallon. And we've managed to hit 5.0 miles per kilowatt hour. And I tell you, with that, everything gets better. But my holy grail is 6 miles per kilowatt hour, which is very close to a beautiful metric equivalent, which is 10 kilometers per kilowatt hour.
Oh, yeah, so you get that nice
because
round
this is
number.
sort of imperial and a metric hybrid.
Because with this, like the watts per mile, the lower the number, the better the efficiency, which doesn't make, which is, when you tell people, they're like, what? But this, the miles per kilowatt hour, the higher the number of miles per kilowatt hour, the better your car is doing.
And the numbers are weird because you get a car, it ends up, it's got like 347 watt hours per mile, and it's a weird number. Now, actually, what's nice about this is it's almost an order of magnitude less than a gasoline equivalent. So what's an average, if you look at miles per gallon, 30 miles per gallon is not a bad gasoline car. And so actually not a bad electric car is 3.0 miles per kilowatt hour. Terrible gasoline car would be 15 miles per gallon. A terrible electric car, 1.5 miles per kilowatt hour. And a great gasoline car would be 50 miles per gallon. And a great EV, 5.0 miles per kilowatt hours.
So you have this direct, like sort of, at least mind, how people think about when they think about vehicles. Because I think, you do see some vehicles like, well, it gets 600 miles or 500 miles or 400 miles, but it has massive batteries. And I don't think people realize that you keep adding mass as you add more kilowatt hours.
Totally.
Now you're working to move this giant battery at all times.
Totally. So I think there's a complete lack of understanding of the value, because the value proposition here with a gasoline car is usually the performance is better, and where it hits you is in your pocket. You have to pay more at the gas pump, but it doesn't really affect the rest of the vehicle. This, welcome to the weird and wonderful world of EVs, everything gets better with efficiency. You're carrying less batteries, you're carrying less mass, there's more room in the car for legroom, comfort and seating, the braking distances are less, the car just gets lighter and better and more live and agile, and actually performance improves with efficiency. It's crazy. Normally with a gasoline car, you get better performance with less gas mileage. Actually, we've got Sapphire, we get 0 to 60 in 1.85 seconds. It's partly due to its efficiency. Those electrons efficiently burning rubber on the road, giving
Yeah.
extraordinary performance.
And you know, as you get to 6 miles per kilowatt hour,
That's the holy grail.
you can put a smaller battery, which means that vehicle will even go even quicker.
Totally.
And it just,
So my vision for the future is a car of much less range, paradoxically, with a more mature charging infrastructure and with cell chemistry which is accepting of faster rates of charge. And then you could do a car maybe with like 180 miles range. Sounds small by today's standards.
Yeah.
But if you could get to 6 miles per kilowatt hour, that would only require a 30 kilowatt hour battery pack, which is tiny.
Yeah, which is
And that
nothing.
would just sit underneath the front seats of a car, and it would help with safety, crumple zones, and just occupant space. Everything just gets better, and it's that cost down driver that I'm chasing. And people sometimes think, well, Lucid's a relatively high-end product, more affordable than many realize. It's from $69,900, but still, it's like a $70,000 car.
Yeah.
Why, if the price of electricity is say it's 23 cents per kilowatt hour, something like that.
Yeah.
But here in California, and you think, well, if I'm saving 10-15% of that, I'm like saving them just a few cents per kilowatt. Why do they give a damn?
Yeah.
And it's not the 23 cents per kilowatt hour, that's the energy cost. To house that energy, if I used a Bloomberg figure, it's $128 per kilowatt hour at the battery level.
Yeah.
So the battery to house just 23 cents of electricity will cost $128. And I'm getting profound advantages there, which can make the difference of building a car by $5,000 or $6,000. And a good analogy is maybe you've got the drop of water here, you've got the drips of water going in, and here we've got a bucket to house them, like that. There's the drips of water, the whole gallon of water. The gallon of water is going to cost me 2 cents, but the bucket is going to cost me $10. I'm looking at the $10, not the 2 cents, and that is 500 times the content. This is about 500 times the content. But be under no illusion, that adds up. And reducing the amount of energy consumed will help the grid, a very vulnerable grid here in the US, from outages. So don't let's just dismiss the value of less energy. And remember, with achieving the 146 mpge, the 5 miles per kilowatt hour of air pure, we're actually, whatever your journey from A to B, whether it's just from home to the shops, on your vacation, on your daily commute, you'll use less electricity going from A to B with that car than any other car in full production today in the world.
Yeah, because you're just, it's more efficient. It's essentially more efficient, and electricity is less expensive. Even our high California rates, it's still cheaper than the gas prices. Like I think my own analysis of my gas car versus my electric car is 3 times more to drive my gas car 100 miles versus my electric car.
So what I'm chasing is the cost of endowing an electric vehicle with range, whatever amount of range. So it's the cost per mile of range, okay? So the units for that are dollars per mile, okay? And that equals the cost of batteries, and that's in dollars per kilowatt hour. And what makes this formula, this equation work, is you have to divide that by efficiency. And this is the key. There's 2 key EV equations that I've created. And of course, this is in miles per kilowatt hour, okay? And the mathematicians amongst us will say, just to check that the formula works, you can cross out the kilowatt hours and you get dollars per mile. Dollars per mile.
Oh, okay.
So while the world is chasing the cost of batteries, we're chasing efficiency. Now, if this gets better, this still gets better.
Yeah.
So these are synergistic. They will live alongside each other. The cost of batteries, dollars per kilowatt hour, and we're seeing with LFP coming well under $100 now per kilowatt hour.
Yeah.
We used to think, well, asymptotically and in C cylindrical are going to approach $100 per kilowatt hour. We're seeing numbers well beneath that now with LFP, iron phosphate chemistry. But this still has a place.
Yeah.
And this is how we can say, let's look at an example, EV in the future. The small EV has just got 180 miles, okay? And therefore we can do that if I can get 6 miles per kilowatt hour, I can achieve that then with those two inputs. I can achieve that with just a 30 kilowatt hour pack. And that's really going to have a profound impact upon everything, because if you look at, we could probably make that pack for around $4,000.
Wow.
And that's how you make a $25,000 car.
Yeah, and that's sort of the holy grail,
Yeah, totally.
I think, at this point,
That's what
because as for you guys, I mean, you're a luxury automaker, so there's the luxury, that's the market, but going down,
Totally.
being able to, because you need efficiency in order to
Totally.
bring the price down.
So that's why we exist. That's why the company exists. I led a small team that created this company back in 2016, and it was really important not just to make a new car company. We had to create the best technology in the world for two things. First of all, to make what I thought was the best car in the world,
Yeah.
Lucid Air, with the most advanced range, and to show what was possible, to create that range without crazy number of batteries, and then to develop this technology so we can do this kind of stuff in the future. And this is what's really important for mankind and the planet. And the other thing is that this technology has to be affordable. And I was able to demonstrate that in a presentation last week to show that not only is it actually affordable, and we're actually using less expensive materials than the competition. The competition is using crazy expensive materials to catch up with our tech.
Yeah.
It's a pure technology play we're doing.
Yeah.
This isn't about me throwing tons of money at expensive materials and processes. There's no point in doing that.
Yeah.
We've taken this to the laws of physics, and it's a sheer scientific driven endeavor, but the tech is designed for mass production, more than the competition ever is. And that's really important. This is a profound consequence in the future, and that's why Lucid exists. And let me give you a further example of how everything gets better, because we've also got the fastest charging car in the world. And you might say, why is that? And the answer is
Architecture?
efficiency.
Efficiency.
Yes.
But the architecture is
Yes.
Yeah.
So here's the crazy thing, that everybody's measuring charging rates in 10% to 80%, but it doesn't matter, because if you've only got 200 miles range, you're only going to get, what's that, 140 miles.
Yeah.
So what really matters is, what matters with charging speed is, and the units should be miles per minute. That's all that matters. When I've stopped for coffee or a comfort break, that's what matters. And that so often is related just power in, which is kilowatts, not kilowatt hours. That's energy. Kilowatts is the rate of those electrons flowing in. But that really doesn't matter. What matters is you have to multiply that by efficiency. And that, the units for that are miles per kilowatt hour. Okay. And then to make it, this is per hour and this is minutes. You actually have to divide everything by 60, otherwise it doesn't balance as an equation.
Yeah.
And so again, if you actually look at the formula, you can actually knock out the kilowatts again, and this is for 60 minutes. So it's and you see that it's miles per minute. So charging speed in real world is directly proportional to the power input, and it's directly proportional to the efficiency. It's remarkable.
Because if you have, let's say, again, if you have a 200 kilowatt hour battery pack and your vehicle charges at 200 kilowatts, but if you have a 60 kilowatt hour or a 30 kilowatt hour battery pack and it charges at 200 kilowatts, those are vast differences in actual the amount of time that you're spending at the charging station.
And if you're power limited by the dispenser of power, then this has a really significant impact upon the time you've got to charge, because some of the bigger vehicles where you're doing like well under 2 miles per kilowatt hour over like 240 kilowatt hour battery pack. If you've got a lot of power, if you can charge it 300, 350 kilowatts, then the speed isn't terrible, but it's still a third of the speed of our car, because it's a third of the efficiency if you say the power is equally limited. And let me give you an example why this works. If you've got two cars and one is parked here, the purple car, and next to it there's the I shouldn't choose the green car because that implies it's environmentally friendly. There's a red car next to it, blood red, okay, and the purple car can do 5 miles per kilowatt hour, and the red one's only capable of 2.5, which many are, okay? And you put the same amount of electricity, the same rate of flow. There's the station, the electricity's going into each of those. Supposing you've got 300 kilowatts going in there, and you've got the same amount of electricity going in that one. That one is accruing twice the number of miles in any minute that that one is. Same amount of electricity. This one is literally accruing twice the mileage. It's charging twice the speed because of efficiency. So that's why Lucid Air is the fastest charging car in the world.
Cool. Because if this car is 5 miles per kilowatt hour, say it's just for easy math for me, it's a 100 kilowatt hour pack. This has a 100 kilowatt hour pack. You're gonna travel 500 miles versus the 250 miles.
Totally. You're absolutely right. Your math is spot on. Let me show you another thing though, because one of the big misunderstandings is the impact upon pack voltage upon charging speed, and it doesn't matter.
Okay, so this is
I've got ultra-high voltage in the car, and it doesn't matter at pack level.
So I just made a video that said why 800 volt systems are more efficient than 400 volt, and now you're gonna. Okay, all right. So I just want to make sure my video is correct.
But let's so let's compare two different battery packs, and I'm going to make it. Well, we're 924 volts for Sapphire and Grand Touring. But fun fact, we're 756 volts for Touring and 672 for Pure.
Pure, yeah.
And that's because we stack the modules. We have 16 modules for Pure, 18 and 20 for Touring, and 22 for Grand Touring and Sapphire. And they're all 42 volts open circuit voltage. So let's compare what are the pros and cons of voltage on charging. And strangely, you might find it a paradox that I'm saying this, because we've gone for ultra high voltage.
Yes.
And at system level it helps. But actually within the actual battery, it doesn't make any difference.
Because the battery is...
Shall I show why?
Yes.
So the battery you've got some cells put together, right? And we use cylindrical cells like that. I think a little tab on the top, like that. And then we do another one here. It's got a little tab on the top, and we put them like that. And in this case, we're going to connect them together in series, okay?
Okay.
So that's positive there, that's the negative there, we're going to connect them. That's a positive there, that's a negative there, and we're going to connect them. Okay? And so we're going to imagine these are supersized batteries, and each battery is a 400 volt battery. Okay, and there's a 400 volt battery there. Now there's another way we could put two batteries together, like that. Like that. And these are the same supersized batteries. They're 400 volts each. Okay, the magic 400 volt batteries, and we're going to connect them in parallel like that. So this is plus, that's plus, and we're going to connect the bottom there, and that's minus, minus. Okay, so here, well, I'll start with this one.
Okay.
This is going to be 0 volts down the bottom. 0 volts, okay? And here at the top is going to be 400 volts. Okay. Right. And here is going to be 0 volts, okay? And at the top, here is going to be 400 volts. So at the top is going to be 800 volts, okay? Right, now, each of these cells, whether the pack is at 800 volts or at 400 volts, each of these cells just sees 400 volts.
Yeah.
So if I'm a dumb little battery cell inside my car, I don't know whether it's 400 volts or 800 volts that I'm receiving. I see 400 volts on the top.
Yeah.
At the bottom of my shoes, I see 0 volts.
Yeah.
So it's completely agnostic. Those cells just experience the same, and they have the same heating. However, there's another factor here which is argued, and I want to dispel this thing.
Okay.
Because what we're going to do is say power is volts times current. Okay. Okay. So that's volts, and that's amps. Okay. Now we know that because V equals IR, which is Ohm's law, we know that power losses, heat, you can derive from those two formula there. You can heat is I squared R. So we know current squared is the terrible thing. So let's have a look at this, and you think, well, hang on. So what I've got here, this has got a resistance R, and that's R ohms, okay? And this has got the same resistance R ohms. So then if you look at between those two, you've got 2R resistance in ohms, because you've got to add them up. The electrons are going to flow through that, then that, right? Now let's have a look at this here. This is R ohms, and this is R ohms. And if you look at the whole system, the electrons can go either way. So if you look at the whole thing, if you look at the resistance, let me just rub that out to make some room. If you look at the system level here, it's R upon 2 ohms. And you'd say, oh, so actually that's got a lot less resistance than that. However, this system is only operating at 400 volts, so it's got to have twice the current.
Because you have to increase the current.
Right.
Yeah.
So twice the current. So the ratio between that and that is 4:1, because that's 2R.
Yeah.
So this has got 4 times the resistance. Okay? So it's resistance times 4 compared with that. But it's got half the current. So it's I times a half. And therefore it's I squared times 1/4. Quarter times 4 is 1. They're exactly the same heating losses. So in terms of what the cell experiences, it's identical.
It's identical.
And what at system level heating losses, it's identical whether it's a pack at 400 volts or 800 volts. It doesn't make any difference. So there's this crazy myth that higher voltage systems will lead to faster pack charging, and at cell level it doesn't.
So at the cell level, it doesn't matter. The rest of the vehicle becomes more efficient because it's lighter. But at the cell level,
That's right.
If parallel or series, you're like
It all cancels out.
It all cancels out. Interesting. Yeah, because my understanding was that if it's 800, then at the cell level, even at the cell level, it is.
Where it makes
I was wrong.
It makes a difference when you're actually at the actual charging dispenser.
Yeah.
Because if you look at, say, a supercharger, V3 level supercharger, which runs at notionally 400 volts, but it can go a bit higher to be fair.
Yeah.
Compare that with a 924 volt Lucid Air Grand Touring, you see about 1/5 of the heat losses with I squared R through the cabling, and that is quite significant. So it's the cable and connector and the route through the car into the batteries, and then all these little connections between the batteries, they add up as well. It's just at cell level, it doesn't make any difference.
Doesn't make a difference at the cell level.
But there's an incremental that now, you can actually offset the I squared R by, you can go down with R. You can say, all right, I'll take the hit with I squared and I'll make the resistance 1/4. So you can make your copper 4 times thicker. That would make 1/4 of the resistance.
Yeah.
So we don't want the copper 4 times thicker. And actually in the pack, we don't use copper at all. We use aluminum, and there's a reason for that. If you look at the conductivity for all different metals, the best metal as a conductor for even gravimetrically is silver. And when we did motorsport battery pack, I asked the team, should we be using silver for the battery connectors? If you want to go for the best, and you rule out silver because of cost, and then you get 2 options, copper or aluminum. And copper makes more sense where you're really constrained in terms of space down to the last millimeter. The extra conductivity of copper is superior if you are volumetrically constrained. But gravimetrically, aluminum is much better if you've got even extra millimeters. And so that's why we use aluminum extensively within the pack for connections. And then we've got some particular high current applications, we switch to copper. And no silver, because I'm not going to use esoteric expensive materials.
Silver's been good. Here's my $400,000.
That's even better than gold.
30 kilowatt hour pack
some
vehicle.
People think gold's the best, but actually silver's the best.
Oh yeah, that makes sense. That's gold. The malleability of gold is to make it stronger, you have to keep adding elements.
You have to alloy it.
You have to alloy it, and then that kind of negates the whole point of using
That's
gold.
why high-end watches never tend to be 24 carat, they tend to be 18 carat. Because they're just so slow.
I just paid all this money for a broken watch. Well, thank you so much, Peter, for talking to us today about efficiency. I really appreciate it. And we'll keep an eye out for...
It's a fun topic, isn't it?
Yeah.
I mean, I think that I can give you some other little nuggets. Tyres play a huge role in the overall efficiency of the vehicle, particularly tyre pressure as well. And then you can go into a nice benevolent circle. If you've got less batteries, you've got less weight, so your tyre spec can come down. And so that helps. So it's a benevolent circle. Interestingly, wheel bearings have play quite a role.
That makes sense. I mean, there's so many little things that you don't really think about when it comes to vehicles and efficiency.
In a former life, I used to, as a design engineer, I used to design hubs and wheel bearings. If you look at a vehicle hub, tends to be there. And we tend to put angular contact wheel bearings here, and then there's the outer race of the bearings here and here. And this fits into an outer race of the hub unit. Okay. Like that. So there's a key geometrical feature within the bearings. These are angular contact ball bearings. People used to use taper rollers and the like. But there's this core geometric relationship within the hub unit. We use a Generation 3 hub unit. And if you want to create a Formula One car, you'd make this angle extremely large. And that will give you incredible camber stiffness of your wheel.
Yeah.
But it's not just the camber stiffness that the wheel bearing gives you. It also gives you turn-in response, particularly on center steering feel. And there's a trade here which is worth maybe 25, 30 miles of range.
Oh, wow.
On turn-in response in steering feel. And we take a very sort of nuanced view of that to get incredible steering feel matched with incredible range. We could go freer rolling and get more range, but we compromise steering feel. You can go completely nerdy on steering feel. And it's not through traverse steering feel, it's on center, because that's when any slack in the bearings winds up and comes on. And you can just feel it. I've done countless test rides just to fine-tune things like this. So the other thing is aerodynamics is so misunderstood. Everyone talks about CD, but it's CDA that matters, because there are two factors to aero drag. One is shape and one is size. You could make a model of a Lucid Air, and it's a tiny model. It's going to have tiny wind resistance. It's going to have notionally the same CD, because it's the same shape. So you need to multiply CD by A, CDA. And our A is exceptionally small because the car is so low and so intensely packaged. So just by virtue of our drive units being smaller, they help make the car more efficient, more aerodynamically, because you can sit in the car lower, and you can go lower in. That's why some people complain they bend their head when they get in the car. And they said, you made a mistake. It was quite intentional. I tell you, it was the price you pay to get 500 miles range.
Yeah, because you want to that's close to the,
we
to
knew
the ground as
it
well.
Yeah.
There's a reason why those F1 cars are like on the essentially below ground. When you get into
Totally. Well, actually, they're terrible for CDA because they're all about downforce to
drag. Because
they're
just trying to they're trying to push that.
But we've got
down
1.197 CD. We've got exceptional A as well, which puts us like 12% ahead of the closest competitor. And we've done back-to-back tests in the winter, and that doesn't. You don't see that 12% difference in CD, but you see it in CDA.
Because in CD, it's like that point, that tenth of a decimal point. You're like, oh, okay. But with the CDA, you're getting a more rounded and holistic look at what's going on with the vehicle.
Yeah. And then, of course, what we've done, we've initiated the Vision 6 project within the company, chasing down, is it possible to get to 6 miles? We didn't know 5 miles per kilowatt hour was possible, but I think it's incumbent upon us to really push the envelope. Someone needs to do this. Someone needs to be crazy enough to do this. And it used to be another company, but it's us now. It's down to us to save the planet.
And so the Project 6, it's a bold undertaking.
Yes. So it was bold, and I've got to tell you, I was mega before anyone was mega, because I've been making electric vehicles great again.
Yeah, mega. So Project 6. What do you think the timetable is at? Couple years?
I don't know.
It's a lot.
It's a huge. We may not be able to do it. We don't know.
We don't know.
No.
But something you have to try.
Yeah. So it's loads of interesting things: aero, regulations, Little things like we're looking at different oils, lubrication oils, different pumping regimes for the oils, looking at different algorithms for controlling the way the magnetic flux flows around the rotor. Now, some of that is actually a gift, because remember, we're getting 5 miles per kilowatt hour at 420 miles range.
Yeah.
If we drop that to 320 miles range, instantly we get more than 5.
Yeah.
It's not just that we've got 5 miles per kilowatt hour. We're doing that with more range than anyone else has got at 420. There's not a single competitor that can do that in the class of vehicle. So if we went to like 250 miles range, we'd have a much smaller battery pack, save the weight, and instantly we'd be over 5.
Yeah. Yeah.
So I don't think that's cheating. I think that's a tool we can use.
Yeah.
So there's no surprise, we're already over 5 in our prototype Vision 6 car.
So, excellent. Well, thank you so much,
Thanks
Peter.
so
I
much.
really appreciate it. I love talking to you.
Yeah, it's
I always feel like I'm learning all the things I probably should have learned in college.
We're all learning.
We're all learning.
Yeah.
Thank you so much for watching. Here we go. For more videos like this with Peter talking about efficiency, sustainability, be sure to subscribe to SAE International.